Hello, and welcome to Quiet Learning for Sleep. This is your peaceful space to unwind, to let go of the day, and to drift into deep, restful sleep while learning softly about our universe. Here, we take gentle journeys through calm ideas, stories from science and nature, space and time, history and life, all whispered at a soft pace, without rush, without noise, and without pressure. You do not need to focus or remember anything. This is learning the quiet way, where your mind floats and drifts and rests, while curiosity stays softly awake in the background. If you'd like, before you get comfortable, you can subscribe and gently like this video. Doing it now means you won't forget later, and it helps others like you find this calm, sleepy corner of the world. Now, allow your breath to slow just a little. Let your shoulders relax. Let your thoughts soften, like clouds drifting across a calm evening sky. There is nowhere you need to go, nothing you need to do, and nothing expected from you here. This time belongs to rest, comfort, and gentle curiosity. And if you drift to sleep along the way, that is not only allowed, it is welcome. So settle in, let yourself melt into stillness, and allow your mind to float quietly as we begin. Before anything familiar existed, before stars burned, before planets formed, before atoms came into being, the universe was a silent ocean of pure energy. There were no structures, no particles, no directions, no time in the sense we know it. Everything was compressed into an unimaginably dense state, a single shimmering field of possibility. And then, with expansion and cooling, that smoothness fractured into patterns so delicate and precise that they would eventually give rise to galaxies and life. For the first tiny fraction of a second after the Big Bang, the temperature was so high that particles could not hold their identity. Quarks, electrons, and neutrinos flickered into existence, only to dissolve back into the energy around them. Space itself behaved like a fluid, expanding faster than light, stretching quantum fluctuations into the seeds of future structures. In those first instants, the universe was not a collection of things. It was a set of rules waiting to be expressed. As the universe continued to cool, something remarkable happened. Energy began to crystallize into form. Quantum fields that had been unified started to differentiate. What we now call the strong force, the electromagnetic force, and the weak force began to separate, each taking on its own identity. And from this separation, particles emerged, stable ripples in these new fields, vibrating with patterns that would endure for billions of years. To understand this quantum world, imagine that space is filled not with emptiness, but with invisible oceans, fields that exist everywhere, even in the vacuum. Each type of particle is a ripple in one of these oceans. An electron is not a tiny marble circling a nucleus. It is a rhythmic vibration in the electron field. A photon is a disturbance in the electromagnetic field. Quarks, neutrinos, gluons, and others each arise from their own fields. All matter, all light, and all interactions are expressions of these invisible, ever-present seas. At this scale, the concept of solidity disappears. What we call matter is mostly space, shaped by the forces that govern how fields interact. Your hand, your breath, your heartbeat, these are patterns held together by the quiet choreography of quantum rules. The solidity you feel is an illusion, created by electromagnetic repulsion. The colors you see are the energies of photons exciting electrons in atoms. The warmth you feel is molecules vibrating with quantum motion. Even stillness is motion here, for nothing in the quantum world is ever truly at rest. One of the most profound ideas in quantum physics is uncertainty. The Heisenberg uncertainty principle tells us that certain properties, like position and momentum, cannot be known simultaneously with perfect precision. This is not a limitation of measurement. It is a statement about the fabric of reality. A particle does not sit in one exact spot. It exists as a cloud of possibility, a wave of potential outcomes. Only when it interacts with something else does it take on a definite position. Reality, at its smallest scale, is a dance between possibility and realization. This uncertainty is the reason atoms are stable. Electrons do not collapse into the nucleus because their wave-like nature spreads them out in space. They occupy orbitals, regions of probability, where their presence is allowed by the quantum rules. These orbitals form the structure of all chemistry. Without uncertainty, atoms could not exist. Molecules could not form. Life could not arise. Uncertainty, far from being chaos, is the quiet foundation of order. Another cornerstone of the quantum tapestry is wave-particle duality. Everything, electrons, photons, even large molecules, can behave as both particles and waves. In the famous double-slit experiment, a single particle sent toward two slits behaves like a wave, creating an interference pattern. But when observed, it chooses a single path, acting like a particle. This dual nature is intrinsic to the quantum world. Entities are not one or the other, but both, depending on how they are measured. Even emptiness is not empty. The quantum vacuum is alive with activity. Fleeting pairs of particles and antiparticles appear and vanish in unimaginably short intervals. These fluctuations give rise to forces, shift energy levels, and influence how particles move. The vacuum is a restless sea, overflowing with hidden motion, shaping everything that happens in the visible world. When you look into the night sky and see darkness, you are looking not into emptiness, but into a humming field of potential. In this series, we will explore the particles that arise from these fields, each one with its own character, purpose, and role in shaping the universe. We will meet quarks, the building blocks of protons and neutrons, bound together so tightly that they can never escape one another. We will meet leptons, the family that includes electrons, and the elusive neutrinos that pass through your body by the billions each second. We will discover bosons, the carriers of forces that allow particles to interact. Photons, gluons, W and Z bosons, and the Higgs boson. We will also explore how these particles behave together, how quarks combine into the atomic nucleus, how electrons shape the personality of matter, how neutrinos drift silently through space as cosmic messengers, how gluons hold the strongest force in the universe, how the weak force allows stars to shine by transforming particles deep in their cores, how photons carry light across cosmic distances, preserving the history of the universe, and how the Higgs field grants mass to particles, allowing structure to exist. Everything we will discuss begins with the quantum tapestry, the vast network of fields and probabilities that emerged in the early universe. These particles are not isolated entities, but expressions of those fields, vibrating in harmony or conflict. Their interactions shape every level of existence, from the smallest atomic structures to the largest cosmic formations. You are built from these interactions. Every atom in your body, every chemical bond, every electrical impulse in your brain is the result of quantum choreography. As you prepare to drift deeper into this series, imagine the universe not as a place filled with objects, but as a grand symphony of vibrations. Each particle is a note. Each interaction is a chord. Each force is a rhythm that holds the pattern together. In the chapters ahead, we will explore these notes one by one, uncovering how the smallest pieces weave the largest story. For now, rest in the knowledge that beneath all matter lies a quiet, shimmering tapestry, one that has been unfolding since the first breath of creation, one that continues to vibrate within you at every moment. To understand matter at its most fundamental level, we must descend into a realm smaller than atoms, smaller than protons and neutrons, smaller even than anything we can observe directly. This realm is where quarks reside, tiny, restless particles impossibly difficult to isolate, yet responsible for nearly everything with structure in the universe. If the quantum tapestry forms the background of reality, quarks are its first threads, woven so tightly that they shape the skeleton of matter itself. Quarks are unlike any other particles. They are the only building blocks that carry a special kind of charge known as color charge, which has nothing to do with visible color and everything to do with the strong force, the most powerful interaction known. There are 6 types, or flavors, each with its own mass and personality: up, down, charm, strange, top, and bottom. These names may sound whimsical, yet each flavor plays a role in the universe's deeper story. And although all 6 exist, only 2, up and down quarks, form the world you experience. Up quarks and down quarks combine to form protons and neutrons. A proton is made of 2 up quarks and 1 down quark. A neutron has 2 down quarks and 1 up quark. These combinations are no accident. They emerge from the strict rules of the strong force, which binds quarks together in precise groupings called baryons. If quarks attempt to combine in any other way, the mathematics of the strong interaction simply does not allow the structure to exist. It is as if the universe has chosen a limited set of stable chords in its quantum symphony. The strong force that binds quarks together is mediated by gluons, particles of pure interaction, carrying color charge between quarks like threads of tension. Unlike photons, which simply pass between charged particles, gluons actively participate in the thing they create. They pull quarks together with such overwhelming strength that quarks can never escape one another. This property is known as confinement. No matter how much energy you put into pulling quarks apart, the strong force simply grows stronger, like a stubborn spring that resists being stretched. If you were somehow able to pull 2 quarks hard enough, you would not separate them. Instead, the energy you put in would create new quark-antiquark pairs, forming entirely new particles. The universe protects quarks from isolation. They are always found in groups, never alone, never free-floating. This rule has never been broken in any experiment, no matter how powerful. In a way, quarks are the universe's most social particles, forever bound in trios or pairs, their identity inseparable from the relationships they form. These relationships give rise to the particles that make up atomic nuclei. Baryons, made of 3 quarks, include protons and neutrons, the foundation of all atoms heavier than hydrogen. Mesons, made of a quark and an antiquark, exist fleetingly in nature and are crucial in mediating forces within the nucleus. Without these combinations, atoms could not exist. Quarks form the architecture that every structure depends on. Stars, planets, oceans, and even the cells of your body owe their existence to these microscopic triplets, humming with energy deep within atomic cores. Most of the mass of a proton or neutron does not come from the quarks themselves. Up and down, quarks are incredibly light, almost ghostly, contributing only a tiny fraction of a proton's mass. The rest, the overwhelming majority, comes from the energy of the strong force binding them together. In other words, the weight of everything you see arises from motion and tension, not from the particles themselves. You are built not from solid matter, but from the swirling energy of a force field that never rests. The other quark flavors, strange, charm, bottom, and top, play different roles. Strange quarks appear briefly in high-energy environments, like the hearts of dying stars or particle accelerators on Earth. Charm and bottom quarks are heavier, forming rare particles that exist for fractions of a second before decaying. And then there is the top quark, the heaviest elementary particle ever discovered, so massive that it decays before it can even form a bound state with others. These heavier quarks influence the universe indirectly, shaping cosmic events during the early moments after the Big Bang, and participating in processes that help scientists probe the deepest layers of quantum reality. Quarks also carry fractional electric charge, another unique feature. Up-type quarks carry a charge of +2/3, while down-type quarks carry -1/3. These fractions combine to give whole number charges to protons and neutrons. It is an elegant balance. The proton's +1 charge arises naturally from 2 up quarks and 1 down quark, while the neutron's neutrality comes from the opposite combination. These charges are not arbitrary. They are built into the architecture of the universe, dictating how atoms form, how chemistry works, and how life becomes possible. Inside a proton or neutron, quarks do not sit quietly. They vibrate, surge, and exchange gluons at nearly the speed of light. This internal motion is so intense that it creates a sea of short-lived particles, quark-antiquark pairs, flickering in and out of existence. The proton is not a static object. It is a storm of quantum energy, constantly shifting, constantly alive. The stability you feel when you hold a stone or touch your table is built atop this ceaseless turbulence. In the early universe, quarks roamed freely in a quark-gluon plasma, a hot, dense state where the strong force behaved differently, allowing quarks to move without confinement. This plasma filled the cosmos in the first microseconds after the Big Bang. As the universe expanded and cooled, quarks became trapped within protons and neutrons, locking the structure of matter into place. The transition from quark-gluon plasma to confined quarks is one of the great phase changes of history, comparable to water freezing into ice, but on scales more fundamental and transformative. Even today, scientists recreate this ancient plasma in particle accelerators, smashing heavy ions together at near light speed to momentarily melt protons and neutrons, back into their constituent quarks and gluons. In those tiny flashes, lasting trillionths of a second, we glimpse what the universe looked like before matter took shape. These experiments reveal how quarks behave under extreme heat and pressure, offering clues to the earliest moments of time and the deep structure of the strong force. Despite their complexity, quarks are everywhere. Every proton in every atom of your body contains 3 quarks. Every neutron contains 3 more. Every heartbeat, every breath, every thought is accompanied by the silent motion of quarks vibrating inside billions of nuclei. They are the foundation on which atoms stand, the hidden scaffolding that allows matter to take form. Without quarks, there would be no nuclei, no atoms, no chemistry, no stars, no planets, and no life. Quarks remind us that the universe is not built from simple pieces, but from relationships. They have no meaning alone, but only in the structures they create together. Protons and neutrons are not passive containers for quarks. They are dynamic, living systems of interaction. And those interactions will shape everything else in this series. The electrons that dance around atoms, the photons that carry light, the weak force that transforms particles, and the Higgs field that gives them mass. As you drift into rest, imagine the matter around you, the walls, the air, your own body, not as solid objects, but as vast collections of tiny quark triplets, bound by threads of pure energy. Their motion creates your weight. Their charge creates your chemistry. Their structure creates your form. Quarks are the quiet architects of existence, hidden from view, yet essential to everything. In the next chapter, we will meet the particles that orbit these quark-built structures, the leptons, the wanderers of the quantum world, and discover how they bring personality and complexity to matter. If quarks form the tightly bound skeleton of matter, leptons drift like free spirits through the spaces in between. They do not feel the strong force. They are not glued into the cores of atoms. Instead, leptons move lightly through the universe, slipping past the turbulence of quarks and gluons with remarkable independence. Where quarks are crowded, noisy, and relational, leptons are solitary. They travel effortlessly, as though gravity and distance have little claim over them. In the quiet symphony of particles, leptons are the soft notes, essential, subtle, and everywhere. The most familiar lepton is the electron. It is so deeply woven into our understanding of matter that we sometimes forget its strangeness. The electron has no known size, no internal structure, no hidden components. It behaves like a perfect point, a tiny charge wrapped in pure probability. Yet it dictates the architecture of every atom, every molecule, every chemical reaction. Electrons determine how elements bond, how metals conduct, how light interacts with matter, and even how your brain sends signals. Without them, chemistry would collapse into chaos. The universe would be dark and silent. Electrons orbit atomic nuclei not as little planets, but as clouds of possibility, regions where the electron might be, shaped by mathematical waves. These waves interfere with one another, stacking, folding, and forming stable patterns called orbitals. Each orbital is like a note on a cosmic instrument, a vibrational mode that determines how atoms behave. The periodic table is not an arbitrary arrangement. It is the direct fingerprint of the electron's quantum geometry. But the electron is only one lepton among 6. Its heavier cousins, muons and tau particles, are like brief echoes of the electron, identical in charge and behavior, but vastly more massive. A muon weighs about 200 times more than an electron, and the tau weighs almost 3,500 times more. They are unstable, decaying in fractions of a second into lighter particles. Their short lives make them rare in everyday conditions, yet they appear constantly in the upper atmosphere, born from cosmic rays, striking Earth's magnetic shield. Every minute, hundreds of muons pass harmlessly through your body, unnoticed, like whispers from the sky. These heavier leptons play a quiet but powerful role in the universe's evolution. In the early moments after the Big Bang, when temperatures were unimaginably high, muons and taus were as common as electrons. As the universe cooled, they vanished, decaying into neutrinos and electrons, leaving behind only faint imprints in the cosmic background. But their presence influenced how matter clustered, how energy flowed, and even how the first atoms formed. They were brief visitors, but their contributions remain built into the universe's structure. Then, there are the most mysterious leptons of all, the neutrinos. These particles are so light, so fast and so aloof, that trillions of them pass through your body every second without interacting. They travel through planets, stars, entire galaxies, as if they were barely there. They carry no electric charge, feel almost no force except the weak interaction, and may travel almost at the speed of light. Neutrinos are cosmic messengers, born in nuclear reactions at the heart of stars, in supernova explosions, and in the radioactive decay of atomic nuclei on Earth. Every second, your body is pierced by neutrinos from the sun, streams of them pouring outward from the runaway fusion reactions that keep our star alive. They pass through Earth as easily as light passes through glass. To detect even a handful of them, scientists build enormous detectors buried deep underground, filled with thousands of tons of water or liquid scintillators. When a neutrino interacts with an atom, a rare event, a tiny flash of light appears, a momentary spark in an ocean of quiet. These flashes allow scientists to trace the neutrino's origin, offering glimpses into processes we cannot observe directly, such as the nuclear furnaces at the core of the sun. One of the strangest discoveries of modern physics is that neutrinos change identity as they travel. They oscillate between 3 types: electron, muon, and tau neutrinos. This shape-shifting behavior implies that neutrinos have mass, although incredibly small. Their mass is so elusive that physicists still cannot pin down exact values. But the very existence of neutrino mass changed our understanding of the universe, suggesting that the standard model of particle physics is incomplete. Neutrinos may hold clues to why matter exists in greater abundance than antimatter, why galaxies formed as they did, and what lies beyond the theories we know. Leptons, unlike quarks, do not feel the strong force. They are comfortable alone. Electrons wander the space around the nucleus. Neutrinos drift effortlessly across cosmic distances. Muons and tau particles appear briefly and vanish again. This independence makes leptons essential to every level of physics. They balance the electric charge of quarks inside atoms. They participate in radioactive decay, enabling elements to transform. They generate electromagnetic radiation when accelerated. And neutrinos, faint though they are, influence the cooling of stars, the dynamics of supernova explosions, and the distribution of matter in the cosmos. Despite their independence, leptons interact with the universe in profound and delicate ways. The structure of atoms depends on the balance between electrons and protons. Without the lightness of electrons, atoms would collapse into dense neutron-like spheres. Without their negative charge, chemistry would have no foundation. Without their quantum orbitals, life's molecules, DNA, proteins, water, could not exist. The electron's small mass allows atoms to breathe, to vibrate, to form complex shapes. It is the electron that gives matter its personality. Muons reveal hidden aspects of nature through their interactions with magnetic fields, offering subtle clues about forces we have not yet discovered. Experiments like muon G2 measure the tiny wobble in a muon's magnetic moment, comparing it with theoretical predictions. A small discrepancy might suggest new physics, perhaps unknown particles or interactions beyond the standard model. Leptons, in their lightness and fragility, may be guiding us toward discoveries waiting just beyond the edges of our equations. Tau particles, heavy and short-lived, act as gateways to rare decays. Their interactions produce cascades of lighter leptons and quarks, allowing physicists to explore the complex interplay of fundamental forces. The tau's mass makes it sensitive to certain processes that the electron and muon cannot probe. Every decay is a tiny message from the quantum world, a hint about how particles communicate, transform, and exchange energy. The story of leptons is one of subtlety. They do not bind into nuclei, but they bind the universe together. They do not roar through the cosmos, but they whisper its secrets. They fill every breath of space with a quiet presence. The electrons in atoms, the neutrinos streaming from stars, the muons falling from the sky. They are the gentle threads that give matter flexibility, motion, and complexity. Without them, matter would be rigid and silent. With them, the universe comes alive. As you rest, you might imagine the invisible dance of leptons around you, electrons humming quietly in their orbitals, shaping the chemistry of your body. Neutrinos passing through you, like soft breezes from distant stars, moons drifting down from space, silent passengers of cosmic storms. These particles, delicate and almost intangible, give form to everything you see and everything you are. And in the next chapter, we will turn to the force that keeps leptons in balance and shapes their interactions, the electromagnetic force, carried by photons, the particles of light. Among all the particles that weave the story of existence, photons are the ones you encounter most often, yet notice least. They illuminate every moment, carry every color, reveal every shape. They bring warmth from the sun, allow your eyes to see, and transfer information across the universe at a speed no other particle can match. Photons are massless, timeless travelers, packets of pure energy that never rest. In the quiet hours of the night, when light dims and shadows lengthen, it is still photons that whisper across the darkness, connecting you gently to the wider cosmos. A photon is the simplest particle imaginable. No mass, no electric charge, no size. It is a ripple in the electromagnetic field, the same field that governs the behavior of electricity and magnetism. And yet, from this simplicity arises infinite variety. Every color of light, every radio wave, every X-ray, every spark of static electricity, these are all expressions of the same particle. What changes is only the photon's frequency, a measure of its energy. High-frequency photons blaze as ultraviolet rays or X-rays. Lower frequencies drift softly as microwaves or radio waves. All belong to a single spectrum, the electromagnetic spectrum, spanning energies vast and small. Photons are born whenever charged particles accelerate. When an electron changes energy levels in an atom, it emits a photon. When electric currents move in wires, they generate radio waves. When particles collide in space, flashes of gamma rays erupt outward. Every star is a forge of photons, releasing them in a constant stream, as nuclear fusion stirs the heart of each star. Many of these photons have traveled for millions or billions of years, crossing the vacuum to reach your eyes. Each one carries a message, a memory of where it came from, a silent record of distant events. But photons are not just carriers of light. They are the mediators of the electromagnetic force, the interaction that governs electricity, magnetism, and the structure of atoms. When an electron feels the presence of a proton, it is photons being exchanged that create the pull between them. This exchange happens constantly in a ceaseless flutter of virtual photons that exist only for a fleeting instant. These virtual photons form the glue that holds atoms together. Without them, electrons would drift away, and matter as we know it would dissolve into a diffuse cloud. The electromagnetic force is long-ranged, reaching across empty space with ease. It shapes the structure of molecules, the behavior of light, and the patterns of chemical reactions. It governs the beating of your heart, the functioning of your nerves, and the glow of every star. It is, in many ways, the force of everyday life, the interaction that makes the world visible, tangible, and richly textured. Gravity may shape the large-scale structure of the cosmos, and the strong force may bind quarks inside nuclei. But electromagnetism governs the realm of experience. A remarkable property of photons is their speed. They always travel at the cosmic speed limit, nearly 300,000 kilometers per second in a vacuum. Massless particles cannot slow down or speed up. They simply exist at this velocity. Time, from a photon's perspective, does not pass. A photon born in the core of a star, and a photon reaching your eye after billions of years, experience that journey as a single, unbroken moment. They are the closest thing the universe has to pure immediacy, bridging distances without aging. Light does not always move through space freely. In materials like glass, water, or air, photons can be absorbed and re-emitted by electrons, effectively slowing their progress. This interaction bends light, creating refraction, the reason a straw looks bent in water, or why lenses can focus images. In metals, photons interact so strongly with electrons that they cannot penetrate deeply, causing reflection. In transparent materials, electrons barely impede them, allowing clarity. Every property of light that we see, from rainbows to reflections to shadows, arises from photons, negotiating with matter's electrons. Photons also have a wave-like nature. They interfere with one another, create patterns, and bend around obstacles. They can spread out like ripples or concentrate into narrow beams. The famous double-slit experiment demonstrates this duality. When not observed, photons behave like waves, creating interference patterns. When measured, they behave like particles, arriving as discrete impacts. This dual nature is not a flaw in our understanding, but a fundamental aspect of quantum reality. a reminder that the smallest scales resist simple categorization. Deep in the quantum world, photons also influence the vacuum itself. What appears empty is actually a jittering landscape of fluctuations, where virtual particles flicker into existence. Photons emerge from these fluctuations, and even virtual photons participate in forces, nudging electrons and affecting energy levels. These vacuum effects can shift spectral lines in atoms, subtly altering behavior in ways measurable with exquisite precision. The electromagnetic field is never truly still. Even at absolute zero, energy quivers faintly through space. The cosmic microwave background, the faint afterglow of the Big Bang, is made entirely of ancient photons, stretched by the expansion of the universe, until they cooled to microwave energies. These photons form a bath of gentle radiation that fills all of existence. Each one has been traveling for nearly 14 billion years, a relic of a time when the universe was hot, dense, and filled with glowing plasma. By measuring tiny variations in their temperature, scientists map the structure of the early universe, learning how galaxies formed from ripples in primordial matter. Photons also carry information across the cosmos. When a star is born or dies, when a planet transits its sun, when a galaxy collides with another, photons stream outward in all directions. With telescopes, we intercept these signals, decoding their wavelengths to learn about temperature, composition, velocity, and distance. Light is the universe's autobiography, written continuously, always available for those who choose to read it. Every observation, from the nearest candle flame to the farthest galaxy, is made possible by photons that have crossed unimaginable distances. At the smallest scales, photons can influence electrons so delicately that they create quantum transitions. Laser light, for example, is made of photons that are perfectly synchronized. Same frequency, same direction, same phase. These coherent photons can cut steel, perform eye surgery, measure gravitational waves, and trap atoms in place. Nothing else in the universe has this combination of precision and power. Lasers show how simple photons, when organized, can become tools of extraordinary accuracy. Photons also participate in pair creation and annihilation. Under the right conditions, a photon can turn into a particle-antiparticle pair, such as an electron and a positron. Conversely, when a particle meets its antiparticle, they vanish in a burst of photons. This transformation of mass into energy, and energy into mass, is one of the most profound symmetries of physics, encoded in Einstein's equation, E equals mc squared. Light and matter are not separate categories. They are interchangeable expressions of the universe's energy. In the cosmic hierarchy, the photon's importance cannot be overstated. It governs the fine structure of atoms, carries thermal radiation, enables chemical reactions through sunlight, and fills the vacuum with gentle background heat. Without photons, stars could not shine, planets could not warm, and life could not emerge. Even the simple warmth you feel when sunlight touches your skin is the result of photons depositing their energy, tiny messengers delivering heat across millions of kilometers. As you rest, you might imagine the universe not as darkness dotted with stars, but as a sea of invisible light, radio waves passing through walls, microwaves warming molecules, infrared rays radiating from your own skin, visible light shimmering in your room. Photons move through everything effortlessly, weaving quiet bridges through space and time. They allow the universe to communicate with itself, moment by moment, endlessly. Now that we've explored photons, the carriers of light and the keepers of the electromagnetic force, we will turn to a very different interaction, the weak force. It is subtle, rare, and elusive, but without it, the sun would not shine, and the elements of life would never form. In the next chapter, we descend deeper into the invisible machinery of nature to discover the particles that make transformation possible. If electromagnetism governs the brilliant, visible dance of light, the weak force governs something quieter, deeper, and far more mysterious. The universe's ability to change. It is the force of transformation, the hidden engine that turns one particle into another, allowing matter to evolve. Without the weak force, the sun would not shine, radioactive elements would not decay, and the diversity of elements that fill the universe would never have formed. Everything would be still, frozen in perfect, unchanging symmetry. The weak force is the whisper that breaks that symmetry. Unlike gravity, electromagnetism, or the strong force, the weak force is astonishingly short-ranged. It operates only across distances smaller than the nucleus of an atom, so small that even light cannot trace them directly, yet its effects ripple outward across cosmic scales. A force so faint, so fragile, fuels the warmth of the sun, drives the formation of heavy elements, and shapes the life cycles of stars. It is almost paradoxical. The faintest force is responsible for some of the most essential events in the universe. The weak force is mediated by three massive particles: the W plus boson, the W minus boson, and the Z0 boson. These are unique in the quantum world. Unlike the massless photon, which carries electromagnetism effortlessly across space, the W and Z bosons are extraordinarily heavy, about 100 times the mass of a proton. Their enormous weight is the reason the weak force has such a tiny reach. Heavy particles cannot travel far before decaying, yet their heaviness also gives them power. They can change the identity of particles, turning a neutron into a proton, an electron into a neutrino, or a quark of one flavor into a quark of another. This ability to change flavors is at the heart of radioactive decay. Take a neutron. Inside its nucleus, a down quark can transform into an up quark through the emission of a W minus boson. The neutron becomes a proton. The W minus boson immediately decays into an electron and an antineutrino, which are released into the world. This event, called beta decay, is one of the universe's fundamental transitions. It shapes how heavy elements break apart, how stars evolve, and how radioactive isotopes warm planets and moons. In the sun, the weak force is the catalyst that ignites the fusion process. Hydrogen nuclei must overcome immense barriers to fuse into helium, but without the weak interaction, the very first step, converting a proton into a neutron, would never occur. The sun's warmth, the golden light that bathes Earth, the gentle photons that keep life alive, all of it begins with a single weak force event. Each fusion reaction in the sun's core starts with the weak transformation of a particle. Without this force, stars would be cold and silent. The weak force is also tied to one of the most puzzling aspects of physics: parity violation. Most physical processes treat left and right as interchangeable. If you mirror them, the universe behaves the same. But the weak force does not follow this rule. It has a preference for left-handed particles and right-handed antiparticles. This failure of symmetry shocked physicists when it was discovered. It means the weak force distinguishes between directions in space, caring deeply about handedness, as if the universe itself had a preferred orientation. This asymmetry is a clue that the weak force may be tied to deeper, unknown patterns in physics. The Z boson, unlike the W plus and W minus, does not change electric charge. Instead, it mediates neutral interactions, allowing particles to exchange momentum without altering their identities. Z bosons are responsible for extremely rare interactions, so rare that billions of particles may pass through matter before a single Z-mediated event occurs. Yet these rare interactions help scientists probe the structure of the Standard Model, providing essential tests of how the weak force behaves at high energies. Because W and Z bosons are so heavy, they can only be created in places of immense energy, the hearts of stars, the moments of cosmic birth, or the collisions of particle accelerators, like the Large Hadron Collider. When scientists first detected these bosons in the 1980s, it confirmed a long-suspected idea, that electromagnetism and the weak force are two aspects of the same underlying interaction. At high energies, they unite into a single electroweak force. Only as the universe cooled did they separate, like branches from the same root. This unification is one of the great symmetries of nature, revealing that forces we see as distinct are connected at deeper levels. The weak force also plays a role in the cosmic abundance of matter. Some theories propose that, in the early universe, heavy particles decayed in ways that favored matter slightly over antimatter. Because these decays required the weak interaction, this force may hold the key to understanding why anything exists at all. Without this subtle imbalance, every particle of matter would have met its antiparticle and annihilated into pure radiation. The universe would be filled with light, but empty of structure. The weak force's tiny preference may have been the deciding factor in the cosmic balance of existence. On Earth, the weak force governs the decay of radioactive isotopes deep within the planet. These decays generate heat, driving tectonic activity, shaping volcanic eruptions, and helping maintain Earth's magnetic field. The slow but persistent release of energy from radioactive decay powers geological processes that have shaped continents and oceans. Even the cycles of carbon, oxygen, and nitrogen involve isotopes whose behavior is guided by the weak interaction. Without it, Earth would be a colder, more static world, lacking the dynamic processes that support life. In particle physics experiments, the weak force allows scientists to peer into the realm of neutrinos, whose ghost-like nature makes them almost undetectable. When a neutrino interacts with matter, something that happens only by the weak force, it briefly reveals its identity. These rare events tell scientists how neutrinos oscillate, how they change flavors, and how they carry information from distant astrophysical events. The weak force is the only reason we can detect neutrinos at all, allowing us to listen to faint messages from the hearts of stars, from supernova explosions, and from the early universe itself. One of the most beautiful aspects of the weak force is its relationship with time. Because weak interactions create asymmetries between matter and antimatter, they may hold clues to why time moves forward. Some processes involving the weak force behave differently when the direction of time is reversed, hinting at a deep connection between the arrow of time and the interplay of particles. These asymmetries are tiny, but they echo across the fabric of the universe, contributing to the flow of events, the expansion of the cosmos, and the unfolding of complexity. As you drift deeper into rest, imagine the weak force not as a violent or direct influence, but as a quiet hand guiding transformation. It works softly, invisibly, in the stillness of atomic nuclei. It changes quarks with a whisper. It allows stars to shine through gentle reactions. It mediates the birth and decay of particles, shaping the universe's evolution with subtle persistence. Without it, the cosmos would be inert. With it, atoms change, stars burn, elements form, and life becomes possible. In the next chapter, we will explore the force that competes with all others, yet remains the most mysterious: gravity, a force that shapes galaxies, bends light, sculpts space itself, and reaches across the universe with a hand both gentle and eternal. Gravity is the gentlest of all the forces, yet it shapes the largest structures in existence. It does not roar like the strong force, or whisper like the weak force, or shimmer through space like electromagnetism. Instead, gravity is a constant, patient presence, an invisible hand smoothing the universe into its vast and graceful form. It gathers dust into planets, planets into solar systems, and solar systems into galaxies. It sculpts the paths of stars, bends the journeys of photons, and stretches the fabric of space itself. To rest inside the universe is to rest within gravity's slow and eternal embrace. For thousands of years, humans experienced gravity without understanding it. It was simply the tendency of things to fall, the pull that kept feet on the ground, the factor that shaped the arc of a stone thrown into the sky. But gravity's quiet pull is far more profound. It is not just a force between objects. It is the geometry of space, responding to the presence of mass and energy. This idea, captured in Einstein's theory of general relativity, reveals gravity not as a push or a pull, but as the natural motion of objects moving through curved space-time. When a planet orbits a star, it is following the straightest possible path through a landscape shaped by the star's mass. Imagine space as a vast, flexible fabric. Every object with mass, atoms, planets, stars, black holes, presses into that fabric, creating a depression. Larger masses create deeper wells, and objects nearby slide into those curves. A planet does not circle its star because something drags it along. It circles because the star has shaped the space around it. The planet moves along the geometry carved into the cosmos, the way a marble spirals around a funnel. This curvature is subtle on Earth and gentle in the solar system. Yet across the universe, it orchestrates grand celestial patterns. Gravity is universal. Every particle that carries energy, even a photon, even a neutrino, contributes to space-time's curvature. This means gravity is not optional or selective. It touches everything. It reaches across infinite distances, weakening with separation, but never truly vanishing. Even the faint gravity of distant galaxies pulls infinitesimally on your body. These tiny influences accumulate, shaping the motion of stars in the Milky Way, collecting galaxy clusters into filaments, and arranging the cosmic web that sprawls across billions of light years. Although gravity is the weakest of the four fundamental forces, Its effects dominate the universe at large scales because it cannot be shielded, cancelled, or opposed. Electromagnetic forces cancel out due to positive and negative charges balancing each other. The strong and weak forces act only at tiny subatomic distances, but gravity quietly persists, accumulating its influence across entire galaxies. The Earth orbits the Sun, not because the Sun's gravitational pull is strong, but because there is nothing to counteract it. Gravity acts alone, steady and unbroken across the vacuum. Stars are born through gravity. In the cold darkness between cosmic clouds, hydrogen gas drifts peacefully until gravity nudges it closer to itself. Over millions of years, gravity gathers this gas into denser and denser regions, slowly compressing it until the pressure and temperature rise. When the core becomes hot enough, nuclear fusion ignites, and a star is born. A glowing sphere of light sustained by a delicate balance between gravity pulling inward and fusion pushing outward. Every sunrise, every warm day, every spark of energy on Earth is ultimately a result of gravity's long-form patience, sculpting gas into stars. Planets form from gravity's artistry as well. When a star emerges, leftover dust and ice orbit in a swirling disk. Gravity encourages these fragments to collide gently at first, then merge into larger bodies. Over time, dust becomes pebbles, pebbles become rocks, and rocks become planetesimals, small worlds that grow by attracting more material. Eventually, planets emerge, each with its own shape, composition, and orbit. Every world in the solar system, from Mercury to Neptune, is a gravitational sculpture, an object born from millions of years of quiet gathering. Gravity also shapes time itself. Clocks run slower in stronger gravitational fields. A clock on the surface of Earth ticks slightly slower than one orbiting in space. Deep near a black hole, time slows dramatically, stretching seconds into centuries from an outside perspective. This warping of time is not theoretical. It is measured constantly in satellites, spacecraft, and experiments. Your phone's GPS would fail within minutes if it did not adjust for the difference between Earth's gravity and the weaker field high above the surface. The flow of time is not uniform. It bends according to gravity's contours. Black holes represent gravity at its most intense. They form when massive stars collapse under their own weight, compressing matter so tightly that space-time curves into a bottomless well. At their centers lies a singularity, an exotic region where our known laws of physics break down. Around them swirls an event horizon, a silent boundary beyond which nothing escapes, not even light. Yet black holes are not just cosmic destroyers. They help shape galaxies, anchor the motion of stars, and influence the evolution of the cosmos. Some black holes spin rapidly, dragging the fabric of space itself around them in a graceful twist. Gravity also carries information across the universe through gravitational waves. These waves are ripples in space-time, generated when massive objects accelerate, like two black holes spiraling toward each other. For most of cosmic history, these waves were silent to us, too faint to detect. But in 2015, scientists recorded the first gravitational wave signal, a tiny vibration in Earth's detectors caused by the collision of two distant black holes over 1 billion light-years away. This detection opened a new window into the universe, allowing us to hear cosmic events that emit no light at all. Even the expansion of the universe is shaped by gravity. After the Big Bang, gravity slowed the expansion, trying to gather matter back together. Eventually, gravity and expansion reached a delicate balance, forming the enormous filaments, clusters, and voids of the cosmic web. Galaxies drift along these gravitational highways, gathering where the mass is densest. The large-scale structure of the cosmos, the patterns visible across billions of light years, emerges from gravity acting over cosmic time. At smaller scales, gravity gives weight to your body, anchors oceans to the Earth, and allows planets to retain their atmospheres. It pulls rain from clouds, sculpts mountains and valleys, and governs the tides as the moon's gentle pull stretches the oceans. It influences the migration of animals, the rise and fall of sea levels, and even the rhythm of life itself. Without gravity, ecosystems would unravel, water would drift away, and the delicate balance that sustains life on Earth would collapse. Gravity may also have a quantum aspect, an idea still wrapped in mystery. Some theories propose the existence of a hypothetical quantum particle called the graviton, a massless entity that carries the force of gravity, the way photons carry electromagnetism. If gravitons exist, they would be unimaginably subtle, slipping through matter with almost no interaction. Detecting them might be far beyond our current abilities, but the search for a quantum theory of gravity continues, linking black holes, cosmic expansion, and the deep structure of space-time into one overarching puzzle. As you rest, gravity continues its silent work. It holds your body to the Earth, keeps the air wrapped around the planet, aligns the moon in its slow orbit, and steadies the stars above. It shapes the galaxies that drift through the night, all while you sleep in the gentle well of Earth's curvature. Gravity never hurries, never stops, never tires. It is the quiet architecture beneath everything, the constant, soft framework of the cosmos. The strong force is the mightiest of all the fundamental interactions, a force so powerful that it binds the very fabric of matter together. It holds quarks in place inside protons and neutrons, gluing them so tightly that no amount of effort has ever succeeded in pulling them apart. It shapes the structure of atomic nuclei, fuels the cores of stars, and governs the stability of nearly everything you can touch or imagine. The strong force does not shout across great distances like gravity, nor does it illuminate the world like electromagnetism. Instead, it works in the deepest interior of matter, in realms smaller than imagination, with a power that borders on the astonishing. In the quantum world, the strong force is carried by particles called gluons. Their name comes from their purpose. They glue quarks together, weaving an unbreakable bond between them. Gluons are massless, like photons, yet they behave very differently. Photons simply pass between charged particles, carrying electromagnetic force without affecting one another. Gluons, however, carry their own version of color charge, allowing them to interact with quarks and with other gluons as well. This self-interaction creates a complex, constantly shifting web of force lines, an energetic storm inside every proton and neutron. Inside a proton, quarks are not sitting quietly like stones in a bowl. They race around at nearly the speed of light, pulled by gluons in a perpetual frenzy of movement. The energy of this motion is what gives the proton the majority of its mass. Quarks themselves are surprisingly light. Only a small fraction of the proton's total mass comes from their intrinsic weight. What gives the proton heft is the dynamism of the strong force, the swirling, ceaseless exchange of gluons and virtual particles. In a sense, mass itself, your mass, the mass of mountains, the mass of stars, comes from the energy trapped in this microscopic whirlwind. Unlike other forces, the strong force behaves counterintuitively. When quarks are very close to one another, the force weakens, giving them room to move freely. This phenomenon is called asymptotic freedom. But as quarks try to pull apart, the strong force grows stronger, like a rubber band that becomes more resistant the more it is stretched. This means quarks are forever confined. They cannot escape one another. They cannot exist alone. If enormous energy is poured into trying to separate them, the universe responds by creating new quark-antiquark pairs, splitting the energy into fresh particles rather than allowing a quark to be isolated. This confinement is one of the great mysteries of quantum chromodynamics, or QCD, the theory that describes the strong force. QCD explains the behavior of quarks and gluons through the rules of color charge, red, green, and blue, along with their anticolors. Every stable combination of quarks must form a color-neutral object, much like mixing pigments to create a perfect white. A proton, with its 3 quarks, balances these colors. A meson, consisting of a quark and an antiquark, balances a color with its opposite. Nothing else can survive. The rules are so strict that the universe simply refuses to allow color-charged particles to appear on their own. The strong force also governs the structure of atomic nuclei. Protons, each carrying a positive electric charge, naturally repel one another. Without the strong force, they would fly apart, and atoms heavier than hydrogen would be impossible. But the strong interaction is so potent that it overwhelms electromagnetic repulsion when particles are close enough. Neutrons, which carry no charge, act as stabilizers within the nucleus, allowing the strong force to bind nucleons together more effectively. The stability, radioactivity, and behavior of every element depends on this delicate balance between repulsive electric forces and the binding strength of the strong interaction. At the heart of stars, the strong force shapes nuclear reactions. When protons and neutrons fuse, the strong force snaps them together into a more stable configuration, releasing energy in the process. This energy is what heats the cores of stars, what ignites fusion, and what powers the luminous glow of the sun. The strong force is responsible for the heat in your room, the warmth on your skin, and the light that nourishes plants on Earth. Every fossil, every flame, every spark is ultimately energy liberated by the strong force during nuclear binding. But the strong force's influence extends beyond ordinary matter into exotic realms. In the densest environments known, neutron stars, the force crushes matter into forms barely comprehensible. A neutron star packs a mass greater than the sun into a sphere the size of a city. Under such pressure, protons and electrons merge into neutrons, and the strong interaction binds these neutrons so tightly that the entire star becomes a single, enormous nucleus. Some theories propose even stranger possibilities. At extremely high densities, neutrons might dissolve into a sea of quarks, forming quark matter, an ocean of unbound quarks roaming freely within a collapsed star. If such stars exist, they would be called quark stars, glowing faintly in the depths of the galaxy. Gluons play a crucial role in these extreme environments. Because colors must always balance, gluons constantly exchange color charge between quarks. This continuous swapping creates a fluid of energy so dense that models describe it as strongly coupled. not like a gas, but like a liquid. In high-energy particle collisions, such as those performed at the Large Hadron Collider, scientists briefly recreate conditions similar to the early universe. When heavy nuclei collide at near-light speed, they form a quark-gluon plasma, a short-lived state where quarks and gluons move freely, unconstrained by confinement. This plasma behaves almost like a perfect fluid with near-zero viscosity, a form of matter unlike anything found in the current universe. The strong force is also responsible for the synthesis of heavy elements. While stars produce elements up to iron through fusion, heavier elements, like gold, platinum, and uranium, require environments of extreme pressure and density. These conditions occur during supernova explosions and neutron star collisions. In these cosmic catastrophes, nuclei are smashed together, and the strong force binds them into new, heavier configurations. Every ring of gold on Earth, every atom of iodine in your body, every trace of uranium in ancient rocks was forged in moments of violent stellar collapse, shaped by the strong force's power to bind nucleons together. Even within everyday matter, the strong force leaves subtle signatures. The binding energy of nuclei affects the mass of atoms, influencing chemical behavior and nuclear stability. The arrangement of protons and neutrons determines whether an element is stable, radioactive, or capable of undergoing fission. These nuclear properties underpin technologies from medical imaging to nuclear reactors and shape natural processes like radiometric dating, geothermal heat, and the radiation emitted deep within Earth's mantle. One of the least intuitive aspects of the strong force is the idea that the vacuum itself is active. In QCD, the vacuum is filled with fluctuating fields, quarks and antiquarks appearing and disappearing, gluons twisting and interacting. This churning sea contributes to the masses of particles and affects the forces between them. The vacuum is not empty. It is a restless substrate upon which matter is built. Within this vacuum, gluons and quarks are constantly pairing, annihilating, and emerging again. The strong force is not merely present inside matter, it shapes the very ground state of the universe. The mathematics of QCD is some of the most difficult in all of physics. Unlike electromagnetism, which allows clean equations and simple calculations, QCD becomes intractable at low energies, requiring complex numerical techniques and high-performance computing. Yet these calculations have revealed beautiful structures. The way quarks cluster, the way gluon fields knot themselves into stable configurations, the way confinement builds order from chaos. These insights help us understand not only the structure of matter, but the history of the universe itself. Even your own body is permeated by the strong force. The nuclei of the atoms that make up your bones, blood, and brain are bound together by the same interaction that binds the nuclei in the heart of distant stars. Every second, countless gluons flash into existence inside you, binding quarks in a flurry of motion. You are held together not by solidity or stillness, but by the vibrant, ceaseless activity of fields and particles. In a deep sense, the strong force is the quiet fire within all matter, the internal furnace that gives shape, stability, and mass to the world. As you drift further into rest, imagine this hidden microcosm, the tiny, relentless motion inside every nucleus, the subtle tension of color charge, the threads of gluons weaving the fabric of matter. These motions are far too small to be seen, and far too fast to be felt. Yet they are the foundation upon which the universe builds everything. The strong force is not loud, not visible, not familiar, but it is the deepest binding in nature, holding together the quiet architecture of reality, moment by moment, everywhere you are. Mass feels like a simple thing. It is the heaviness of a stone, the weight of your body, the resistance you feel when you push against the world. It is so familiar that we seldom question it. Yet in the quantum realm, mass is not an inherent property. It is not something particles simply possess. Instead, mass arises from an interaction, an intimate relationship with a field that fills all of space. This field is the Higgs field, a quiet, omnipresent ocean that gives substance to the universe. The Higgs field is everywhere. It permeates every corner of existence, from the vacuum between galaxies, to the air around you, to the empty space inside every atom, even in the darkest regions where photons seldom pass. The Higgs field persists. You are always inside it, moving through it with every breath, every heartbeat, every quiet moment. Unlike the electromagnetic field, which ripples with familiar light, the Higgs field is calm and uniform, a constant presence that shapes matter in ways that are profound yet subtle. Particles acquire mass by interacting with this field. Those that couple strongly to the Higgs field move as though wading through deep water. They feel resistance, and therefore exhibit greater mass. Others interact only weakly, gliding effortlessly, barely slowed. The photon, which does not interact with the Higgs field at all, remains massless and free to travel at the speed of light. Neutrinos, which interact only faintly, carry almost no mass. And heavier particles, like the W and Z bosons, couple intensely, gaining the substantial masses that define the weak force's short range. This idea, that mass is not a built-in attribute, but a consequence of a particle's interaction with a pervasive field, is one of the most elegant insights of modern physics. Before the Higgs mechanism was proposed, the standard model of particle physics struggled to explain how particles could acquire mass without breaking the mathematical symmetries that bind the theory together. The Higgs field resolved this puzzle by providing a way to preserve symmetry while still granting particles their weight. It is a kind of cosmic background that particles must push against in order to exist as massive objects. The Higgs field also has a quantum excitation, the Higgs boson. This particle, discovered in 2012 at the Large Hadron Collider, is a tiny ripple in the Higgs field, the smallest possible vibration of the medium that gives matter mass. Detecting the Higgs boson was like tapping the surface of an invisible ocean and watching it respond. Its discovery confirmed that the field itself is real, a fundamental ingredient of the universe rather than a theoretical abstraction. The Higgs boson is incredibly heavy and unstable, decaying almost instantly into lighter particles. Yet even this brief existence was enough to reveal the underlying mechanism that shapes matter. Most of the mass of your body does not come from the Higgs mechanism. Quarks, for example, are relatively light. Instead, the majority of your mass comes from the strong force, the frantic motion and energy of quarks and gluons inside protons and neutrons. Still, the Higgs field is essential because without it, quarks and electrons would be massless. They could not form atoms. Electrons would not bind to nuclei. Chemistry would not exist. Without the Higgs field, the The building blocks of matter would drift apart like light rays in empty space. There would be no molecules, no stars, no planets, no life. Only a cold universe filled with fleeting radiation. One of the most intriguing aspects of the Higgs field is that it sits in a false vacuum. The universe occupies a state that is stable, but not perfectly so, like a marble resting in a shallow depression rather than at the lowest possible point. Under extreme conditions, or over unimaginable timescales, the Higgs field could shift into a different configuration. Physicists call this vacuum metastability. If such a transition were ever triggered, the laws of physics would change instantly, rewriting the universe in a wave of transformation. Fortunately, calculations suggest the universe is stable for trillions upon trillions of years to come. Still, the concept reveals how delicate our reality is, how dependent it is on the exact shape of a field we cannot see. The Higgs field also influences the early history of the cosmos. In the first fractions of a second after the Big Bang, temperatures were so high that the Higgs field had no effect. Particles moved freely, massless and unrestrained. As the universe cooled, the Higgs field switched on, settling into its present state and slowing particles down, endowing them with mass. This process was not gentle. It was a phase transition, a moment when the entire universe changed character. The Higgs field crystallized into its current form, and in doing so, it shaped the growth of galaxies, the evolution of stars, and the eventual emergence of life. The Higgs field interacts differently with different particles. The top quark, for example, couples to the Higgs field more strongly than any other known particle, giving it a mass nearly 200 times that of a proton. This makes the top quark extraordinarily short-lived. It decays almost instantly. Lighter particles like electrons experience only a mild interaction with the field, giving them the delicate mass necessary for stable atoms. These different couplings are not random. They are embedded in the mathematical structure of the Standard Model, yet their origin remains a mystery. Why does each particle couple with the Higgs field as it does? Why such a vast range of masses? The answers remain hidden, leaving fertile ground for future discoveries. There is also the question of dark matter, the invisible substance that shapes galaxies through its gravitational pull. If dark matter is made of particles, do they interact with the Higgs field? Some theories say yes. Dark matter could acquire mass through the Higgs mechanism, just like ordinary matter. Others suggest dark matter may couple to an entirely different field, forming a parallel sector of physics we have not yet glimpsed. The Higgs field may be only one piece of a larger mosaic, a stepping stone toward understanding a deeper layer of the universe. Even the vacuum energy of the Higgs field shapes the universe. Its value contributes to the cosmological constant, the mysterious force driving the accelerated expansion of space. This connection hints at a profound and unresolved tension in physics. The energies predicted by quantum fields are vastly larger than what cosmology observes. Something is missing in our understanding, something that ties together quantum fields, gravity, and the structure of space-time itself. The Higgs field sits at the crossroads of this mystery, hinting at new physics waiting to be discovered. As you drift further into rest, imagine the Higgs field as a soft, invisible medium, filling all of existence. Picture particles moving through it, some slowed gently, others gliding easily, all shaped by their connection to the field. This interaction gives form to everything familiar: the weight of your body, the solidity of the ground, the structure of atoms and stars. The Higgs field is the quiet, ever-present foundation upon which the material universe stands. All of physics, every force, every particle, every breath of matter, rests within this silent field. And though you cannot sense it directly, you are immersed in it always, held softly by the background that gives existence its substance. At the smallest scales of existence, matter dissolves into something more subtle than particles. The familiar objects of our world, atoms, electrons, quarks, photons, are not tiny beads or specks, but ripples in underlying fields that permeate all of space. These fields form the true foundation of reality, an unseen framework that lies beneath every moment, every object, every breath. This is the world of quantum fields, a quiet, continuous substrate in which everything you know is a vibration, a wave, a disturbance in an ever-present ocean. A quantum field is not a physical surface or a material substance. It is an abstract, mathematical entity that fills all of space, even the darkest voids between galaxies. Every field is everywhere, at every moment. There is an electron field, a quark field, a neutrino field, a photon field, a Higgs field, one for each type of particle. When a particle appears, what you are really seeing is the smallest possible ripple in that particle's field. Particles are quantized excitations, discrete bundles of energy arising from waves in the field. You never encounter a standalone particle. You encounter a momentary vibration in an underlying continuum. This idea that fields, not particles, are the fundamental units of nature is one of the most transformative insights in physics. It means that what appears solid is, at its core, a pattern of disturbances in an invisible medium. When you touch a chair, what your hand contacts is not a collection of tiny objects, but the electromagnetic interactions between the ripples in various fields. When you look at a star, the light that reaches your eyes is a wave in the photon field. When you take a breath, the oxygen molecules entering your lungs are stable arrangements of excitations in the electron, proton, and neutron fields. Everything is a symphony of vibrations layered within one another, interacting and exchanging energy. These fields do not sit still. Even when no particles are present, fields fluctuate with relentless subtlety. This is the quantum vacuum, a restless foam of activity where virtual particles appear and disappear, where energy flickers unpredictably. These fluctuations can influence real particles, shifting their masses and altering their behavior. The vacuum is not empty space. It is an energetic sea, where waves are always present, humming softly beneath the surface of reality. The strength of a field determines how particles behave. The electron field is associated with the electron's charge and mass. The photon field governs the propagation of light and the behavior of electromagnetism. The quark fields interact with the gluon field through the strong force, and the neutrino fields behave with astonishing quietness, interacting so rarely that trillions of neutrinos pass through you, unnoticed every second. Each field contributes unique properties to the particles that appear as excitations within it. Interactions between particles are really interactions between fields. When two electrons repel each other, their fields exchange disturbances, virtual photons, that carry momentum and energy. When quarks are pulled together, gluon fields braid themselves into elaborate patterns. When atoms absorb light, the photon field transfers its energy into the electron field. All forces arise from these exchanges. There is no such thing as a force acting from a distance. There are only fields communicating, merging, shifting, and transferring energy through their overlapping waves. Quantum fields produce all the basic interactions of nature. The electromagnetic field gives rise to electromagnetism. The gluon field underlies the strong force. The W and Z boson fields generate the weak force. And the Higgs field gives particles mass by resisting their motion. Even gravity, the curvature of space-time, may eventually be described by a quantum field, the graviton field, whose hypothetical excitations distort geometry itself. Though unconfirmed, the search for a quantum theory of gravity is one of the deepest quests in physics, promising to unite quantum mechanics and general relativity into a single framework. The interactions of quantum fields create the richness of the periodic table. Hydrogen, with its single proton and electron, is a simple interplay of fields. Helium, carbon, oxygen, and iron arise from more complex combinations, each built from stable arrangements of quark and gluon field excitations. When atoms form molecules, their electron fields merge into shared orbitals. When molecules assemble into cells, the interactions multiply into an intricate network of fields, giving rise to chemistry, biology, and ultimately consciousness. Everything from starlight to DNA is an emergent pattern of quantum fields expressing themselves across scales. Because fields are continuous throughout space, they create subtle connections across distances. Entanglement, one of the strangest aspects of quantum mechanics, arises naturally from the structure of fields. When two particles become entangled, their fields overlap in such a way that their properties remain correlated no matter how far apart they travel. Measure one particle, and the other responds instantly, not through communication, but through the shared structure of the underlying field. Space does not separate entangled particles. The field that defines them remains unified. The quantum vacuum also affects the motion of objects. In a phenomenon called the Casimir effect, two metal plates placed extremely close together experience a force pulling them together. This arises because fluctuations in the vacuum behave differently inside the gap between the plates compared to the surrounding space. Even emptiness exerts pressure. These vacuum effects are not theoretical curiosities. They have measurable impact on atomic energy levels, chemical interactions, and even the stability of matter. Quantum fields also play a role in cosmology. The early universe was a hot, dense soup of fluctuating fields, with particles constantly forming and annihilating. As the universe expanded and cooled, fields settled into stable configurations, giving rise to the particles we know today. Subtle shifts in fields may have influenced inflation, the rapid expansion that smoothed the cosmos. Even today, dark energy, which drives the universe's accelerating expansion, may be a property of the quantum vacuum, tied to energy stored in fields we barely understand. Every field has a characteristic energy, a particular way it prefers to exist. In many cases, these energy levels determine how matter organizes itself. The electron field prefers certain vibrational patterns around the nucleus, creating the discrete energy levels of atoms. The quark fields prefer stable combinations of color charge, creating protons and neutrons. Even the Higgs field prefers a particular non-zero value, much like a stretched membrane that naturally springs into shape. These preferences are not arbitrary. They are encoded in the mathematics of the universe, forming a kind of blueprint for reality. Even your own body, seemingly solid and separate, is nothing but a temporary arrangement of field excitations. The atoms in your cells are stable only because the electron field remains in its ground state, and the quark fields are bound tightly by the gluon field. Your warmth is the result of vibrations within these fields. Your thoughts arise from electrical impulses guided by the electromagnetic field. Your existence is supported by the Higgs field, giving mass to your particles. You are a symphony of fields in perpetual motion, organized briefly into the shape you know as yourself. Quantum fields reveal a universe that is both simpler and more mysterious than it appears. Simpler, because everything arises from the same underlying structure, fields gently rippling through space. More mysterious, because these fields do not behave like anything in our ordinary experience. They are continuous but quantized, restless but stable, abstract yet foundational. They are the hidden architecture beneath every star, every atom, every living being. As you drift into sleep, imagine the world beneath the world, a calm ocean of fields stretching in every direction, reaching into every corner of space. In that ocean, particles rise and fall like gentle waves. Forces emerge from their interactions. Matter forms from patterns in their vibrations. The universe breathes through these fields, quietly, endlessly, with no boundary and no beginning. You are wrapped in them always, held within their subtle structure, resting in the invisible fabric that supports all of existence. As we arrive at the final chapter of this quiet journey, let the universe unfold once more, not as separate pieces or isolated particles, but as a single, interconnected story. Every field, every wave, every particle we've explored rests upon four fundamental forces that shape the cosmos. These forces are the silent rules of existence, the deep grammar that matter follows, the subtle architecture holding reality together. They are the strong force, the weak force, electromagnetism, and gravity. Everything you see and everything you are arises from their patient, consistent work. Picture the universe just after its birth, a formless, brilliant ocean of energy where forces were unified into a single, elegant interaction. Only as the cosmos expanded and cooled did these forces break apart, one by one, like colors separating through a prism. First, the strong force split away. Then the electro-weak force divided into the electromagnetic and the weak forces. Gravity, the most elusive of all, continued shaping space itself. Each separation introduced new structures, new possibilities, new ways for matter to interact. This branching of forces is what made stars possible, made atoms possible, made life possible. The first force, strong nuclear force, is the most powerful in the universe. It acts only across subatomic distances, yet within that tiny range, it overwhelms everything else. The strong force binds quarks together, weaving them into protons and neutrons. It forms the heart of every atom, holding the atomic nucleus together, despite the intense electrical repulsion between positively charged protons. Without this force, matter could not exist. Every solid object, every molecule, every cell relies on the strength of this invisible bond. The strong force is the ultimate sculptor of the nucleus, the quiet architect of stability. But the strong force is also subtle. Its behavior changes depending on distance. At extremely short ranges, quarks move almost freely, as though the force loosens its grip. But as you pull them apart, the force grows stronger, resisting separation with increasing intensity. This is why quarks are never found alone. The field restrains them with unbreakable tenacity. If you try to separate two quarks, the energy you add simply creates new quark pairs, ensuring that confinement remains absolute. This peculiar property, where pulling harder only strengthens the bond, keeps the building blocks of matter tightly bound in every nucleus of every atom in your body. Next is the weak nuclear force, the quiet catalyst of change. Unlike the strong force, it does not bind or hold. Instead, it transforms. It is responsible for radioactive decay, for the conversion of one particle into another, and for the strange dance of neutrinos through the cosmos. The weak force is delicate, operating over incredibly short distances, yet its effects ripple throughout the universe. Without it, stars could not shine. The sun itself is powered by weak force reactions that allow hydrogen nuclei to merge, slowly producing helium and releasing energy that warms Earth. Every sunrise is a gift of the weak force, a gentle whisper from quantum mechanics, fueling the life of worlds. The weak force also shapes the abundance of elements in the universe. In the early moments of the cosmos, it helped determine how many protons and neutrons survived the primordial fire. Later, inside stars, it governs the pathways through which elements are forged. And in supernovae, the explosions that seed galaxies with heavy elements, the weak force guides the transformation of matter under extreme pressure. It is not a force we feel in daily life, but it is the invisible pivot on which cosmic chemistry balances. Then comes electromagnetism, the most familiar of the four forces. It governs light, electricity, magnetism, and all chemical bonds. The electromagnetic force is what shapes atoms, links molecules, and allows matter to form every structure you can touch or see. It holds electrons in orbit around nuclei and determines the geometry of molecules. Your senses, sight, touch, sound, even thought, are all products of electromagnetic interactions. The warmth of your body, the beating of your heart, the firing of neurons in your brain, all arise from waves and charges interacting through this force. The electromagnetic field is also the messenger of the universe. Photons carry its influence across space, traveling at the speed of light. When you look at a star, you are witnessing electromagnetic waves that have crossed unimaginable distances. These waves bring information about distant worlds, letting us study galaxies, nebulae, and the cosmic background radiation. Every telescope, every photograph of the night sky, every spark of electricity, and every ray of light is an expression of this force. If the strong force binds matter, and the weak force transforms it, electromagnetism animates it, bringing energy, motion, and interaction. Finally, there is gravity, the most mysterious of the four. It is the weakest force, yet it shapes the largest structures in the universe. Gravity bends the fabric of space-time, guiding planets around stars and stars around galaxies. It gathers clouds of gas into newborn stars, sculpts galaxies into spirals, and shapes the cosmic web that stretches across billions of light years. We feel gravity constantly, yet we understand it less than any other force. It is geometry itself, space responding to the presence of energy and mass. Gravity operates across all scales. It holds oceans to Earth, binds satellites in orbit, and keeps the moon drifting through the night sky. It causes black holes to form, collapsing matter so intensely that it warps space into regions from which not even light can escape. It shapes the expansion of the universe, and may even be tied to the energy of the quantum vacuum. Gravity, gentle yet inexorable, is the quiet rhythm of the cosmos, an unseen conductor guiding the dance of galaxies. Though these four forces seem different, they are deeply related. In the early universe, they were unified, their distinctions blurred by unimaginable temperatures. As the cosmos cooled, symmetry broke, and the forces separated into the forms we know today. Many physicists believe that at even higher energies, far beyond our current technology, the forces may merge again, revealing a deeper unity. Some theories propose that particles are vibrations not just of fields, but of higher dimensional strings. Others suggest that space-time itself emerges from quantum entanglement. Though we do not yet know the full truth, we sense the connections, like faint constellations in a foggy sky. The interplay between forces is what makes the universe dynamic. In stars, gravity compresses matter, while the strong force resists collapse. The weak force transforms particles, enabling fusion, while electromagnetism carries the energy outward as light. In atoms, the strong force holds the nucleus together, while electromagnetism arranges electrons around it. In chemical reactions, electromagnetic bonds reshape themselves, guided by quantum rules, influenced subtly by the weak force. Across galaxies, gravity draws matter together, while electromagnetic radiation and stellar winds push it apart. The universe is a balance of four voices, each essential to the cosmic symphony. Even you, lying here drifting towards sleep, are woven from these same interactions. The strong force binds the quarks in your protons and neutrons. The weak force played a role in forming the elements that make up your blood and bones. Electromagnetism shapes the atoms and molecules that compose your cells. And gravity holds you gently to the earth as it carries you through space. Every breath, every heartbeat, every thought is a harmony of forces working quietly and faithfully inside you. As your body relaxes, imagine these forces flowing through the entire cosmos, from the smallest particle to the largest galaxy, from the earliest moments of the universe to the present night. Imagine the quiet order underlying everything, the way fields ripple, the way particles dance, the way forces guide their motions. The universe is not chaotic. It is intricate, balanced, elegant, and you are part of it, shaped by the same principles that govern stars and galaxies. The story of quantum fields and fundamental forces is the story of existence itself. It is the gentle hum beneath every atom, the order that allows complexity to arise from simplicity. As you drift deeper into rest, hold on to this quiet truth. The universe is connected. Everything influences everything else. Forces weave the cosmos into a single, unified tapestry, and within that tapestry, you are a luminous thread, unique, necessary, and beautiful. Let that thought settle around you like a soft blanket. Let the universe feel close, steady, and calm. The same laws that guide galaxies gently guide you. The same forces that shape the stars cradle you now. And as your mind drifts peacefully into sleep, remember, in the grand fabric of reality, you are not separate from the cosmos. You are woven into its very essence.
you